Hello. Today I'm going to talk about back query containment and this connection to information theory. This is a talk given at PODS 2020 and it's joint work with Mahmoud Abou-Khamis, Fokion Colitis and Hank No. And my name is Dan Suju. So back semantics simply means keeping the duplicates. This is a standard semantics in SQL. In 1993, Chowdhury and Vardy asked a very natural question. Given two queries Q1 and Q2, check if for any database the result of Q1 is contained inside of Q2 under back semantics. In 1995, Ioannidis and Ramakrishnan proved that containment for unions of conjunctive queries is undecidable. However, the decidability for conjunctive queries has remained open despite a very long, a large number of research on this topic. In this talk, I will talk about the connection between query containment under back semantics and information theory. So let me start with a quick background on query containment under back semantics. We fix a Boolean conjunctive query. The inputs will be sets, will be relations that are sets. However, the answer to Q will be interpreted as a back. Instead of being just true or false, we count the number of homomorphisms from Q into a given database D. In SQL, this can be represented as a select count star query. And we are interested in the back containment problem, which was formulated by Chowdhury and Vardy in 1993. Given two Boolean conjunctive queries, Q1 and Q2, check if for any database, the number of homomorphisms from Q1 to D is less than or equal to that from Q2 into D. And as I mentioned, this problem has been open for many years. The second kind of background that we need is from information theory. I'm going to represent a finite probability space through a relation P. P has n attributes, x1, xn, and every tuple is annotated with a probability such that the sum of these probabilities is 1. We define the entropy of a subset of variables x alpha. So x alpha is any subset of the variables x1, xn. And the entropy of this set is the standard definition. It is the expected value of log of 1 by p of x, where lowercase x, p of lowercase x is a marginal probability of the outcome x of these joint random variables. So there are 2 to the power n possible subsets of the variables x1, xn, which gives rise to 2 to the power n values of the entropy, and they together form a vector which is called an entropic vector. And we are going to denote it with a bold case H. In addition, we are going to use the notation of the conditional entropy, which is just a difference between two entropic terms, namely the entropy of all the variables in x and in y minus the entropy of the variables in x on which we are conditioning. So with these notations, I can define the problem in information theory that we're interested in. Where an information inequality is simply a statement saying that a linear combination of entropic terms is greater than or equal to 0. A max information inequality is simply a statement saying that the maximum of m linear expressions of entropic terms is greater than or equal to 0. And the inequality is said to be valid if and only if it holds for all entropic vectors. For a quick example, this is example 311 in the paper. Here is an inequality that is valid. Notice that we make free use of conditional entropies, which are simply differences of two entropic terms. So this remains a linear expression, which we assert is greater than or equal to 3 times h of all the variables x, y, z. And we can also examine a max information inequality, which would look something like this. So with these notations, we can define the max information inequality problem, IIP without the max and max as IIP with a max, to be given an information inequality with integer coefficients, check if it is valid. And as I mentioned, it is still open to date whether even the simpler information inequality problem without max is decidable. So this was my quick background in information theory. I recommend looking up table 1 in the paper, which has an extensive correspondence between concepts in database theory and those in information theory. So with this background in mind, we can now describe our 3 main results. Our first result says that the back query containment problem when Q2 is acyclic is computationally equivalent by many wand reductions to the max information inequality problem. For the second result, we need some technical definitions. We call Q2 chordal if its Geigman graph is chordal, and we call it simple if any two clicks share at most one variable, which means this tree decomposition is such that any backs share at most one variable. Our second result says that when Q2 is both chordal and simple, then the query containment problem under back semantics is decidable, and it is decidable in exponential time. And our third result is actually something we use to prove the second result. It's a result about information inequalities. Call it such a linear expression simple if all the terms are positive, except perhaps those of single variables. And we prove that under those restrictions, a max inequality problem is decidable in exponential time. So before I highlight some details of these results, I'd like to quickly comment on their significance. Previous work on back query containment by Ramakrishnan, Ioannidis, and Jairam, Kolaitis, and B, and also the recent work by Konstantinidis and Mogavera, they connect back query containment to Hilbert's tense problem. Our connection seems to be novel. We connect it to information inequalities, and it is a strong connection. It is a reduction in both directions. Similarly, in terms of the study of the information inequalities, the only previous connection was known was due to Chan, who has a very direct connection, one-to-one correspondence between information inequalities and so-called group inequalities. Here too, our connection is novel in that it connects this to back query containment. And finally, I want to mention that our decidability class is different from the previous two decidability classes that were known in the literature. So in the rest of this talk, I will highlight some technical aspects of the three results that I mentioned earlier. And I will start with the first one, which is the many wand reduction from back query containment into max information inequalities. And the critical technical nugget here is a beautiful formula introduced by Tony Lee in 1987. It goes as follows. Fix any tree decomposition of Q2 and then order on the nodes of this tree decomposition. We define the following linear expression of entropic terms. We sum over all the nodes of T, and we take the entropic term of the variables at that tree node, at that back, conditioned on the common variables with the parent. So for a quick example, if this is our query Q2, then we start with the first tree node, which is just h of u b, and the second tree node asks us to condition on the variable that is common with the parent, which is u. Kopparkin and Rossmann proved the following sufficient condition for query containment. They considered all homomorphisms from Q2 to Q1, applied each such homomorphism to this expression that had variables from Q2 to convert it into an expression that had variables in Q1. And they proved that if the maximum of these expressions is greater than h of all the variables of Q1, then query containment holds. We proved that if Q2 is acyclic, then this is also necessary. And we also proved that any max information inequality, not just those of the simple form 1, but any max information inequality can be reduced to the containment problem of acyclic query, of two queries where Q2 is acyclic. I want to briefly describe an aspect of the second result. So here we essentially develop a kind of canonical databases that are sufficient to refute containment. We call a relation P a witness for the non-containment if the database obtained by projecting P on the atoms of Q1, please see the details in the paper, if this database is a witness for the non-containment, if the inequality holds in the opposite direction. So we find two interesting kind of witnesses. The first one is a very simple independent relation where the attributes are simply independent. They are Cartesian products of their domains. And the second one is a generalization where we allow dependencies between attributes. Like here, this is a concatenation of U and V. Here, two attributes are repeated. And we prove that if Q2 is chordal and containment fails, Then, if all the clicks of Q2 are disjoint, if they're disconnected, then there exists a product witness, one like here. On the other hand, if the clicks share up to one variable, then there exists a normal witness, like the one here. Sharing at most one variable is the same as saying that Q2 is simple, and this underlines our second result. Finally, regarding the third result, let's define a basic entropic function as here. For each variable xi, we are going to associate with an entropic function that is one if and only if the set of variables on which we are computing contains our distinguished variable xi. The following is known for Scherer's inequalities. Consider a linear expression of entropic terms with positive terms. This is greater than h of all the variables if and only if it holds on all the basic functions. And therefore, it's checkable in polynomial time because there are just n basic entropic functions. We extended this relation by allowing negative terms, but only for single variables. And we proved that this inequality holds if and only if it holds on all exponentially many step functions, which are defined here. And I invite you to take a look at them in the paper. And both results can be extended to max inequalities, but there are some details that I invite you to read in the paper. This is all the time we have. So to summarize, I showed you 3 results, and I'm not going to repeat them here. There are several interesting open problems. In particular, is query containment under back semantics decidable? And also interesting would be, is there a direct link between Hilbert's 10 problem and information inequalities? And on this note, I will stop here.